Welcome back. I've got a really unusual experiment to show you today, and one that you can try at home. You need some quite simple apparatus. What you need is a magnet, but you need one of those magnets that's the really, really strong magnets, the little tiny ones, easy to get hold of, and you've probably got some of these somewhere anyway. I've got a nut here just off a bolt that you might use in any engineering situation, and I've got a frying pan. And the important thing is that the frying pan is not made of steel, because I wanted to indicate to you firstly that this frying pan is made of aluminium, and the proof that it's not made of a magnetic material is if I take the very strong magnet, I can just check that it clicks onto the nut fine. Yes, it does. And then when I take the frying pan, it doesn't stick onto it at all. It doesn't stick onto that side, and it doesn't stick onto this side. But what I'm going to do is I'm going to do some slightly unusual experiments, both with the nut and the magnet on the frying pan, and I'd like you to see if you can explain it. So here's the thin aluminium frying pan. It's a bit of an old one from our house. We don't use it very much anymore, which is why it looks a bit burnt and dirty, but that doesn't matter. It's got a non-stick coating on it. That doesn't matter either. The only thing that's important is that it's not magnetic. And I'm going to do something that's fairly obvious. I'm going to take the nut and just let go and let it slide off the frying pan. I'll just do that again. So there's the nut sliding off the frying pan. Now remember, the frying pan is not magnetic, so let's do exactly the same thing with a little magnet. I'll try that again. I haven't actually changed the angle at all, but it seems to do something completely different. It's actually quite difficult to set the two off at once, but the best way to do that is to sit them next to each other and then just to tilt the frying pan. Now this is really, really strange, and I'm going to show you a few more experiments and then try and explain it to you. So if you remember, in the last experiment we kept the frying pan stationary and we let the magnet slowly slide down it. Friction was absolutely minimal, and yet the magnet moved very slowly. I'm going to do the same experiment but in a slightly different way. This time I'm going to hold the magnet stationary and move the metal. So I've got a sheet of copper here which swings fairly freely. And of course you'll remember that copper is not a magnetic material. And I've got myself a pretty strong magnet. Remember, the frying pan isn't magnetic, but the magnet definitely is. And I'm going to put the magnet's poles on either side of the piece of copper and then just let it swing again and see what happens. Very strange. I'll do that once more. It sort of almost stops immediately. There seems to be a braking force acting on it, which isn't there when I remove the magnetic field. So this really is going to take some explaining, but I think there's some other experiments I can show you first. At this point, it is just worth showing you one more experiment with the copper shape. Here's one with slots cut in it, and it swings freely as the other one did. But see if you can guess what happens when we put it in the magnetic field. And this might surprise you. Doesn't seem to make any difference at all. The only difference we've got here is that the copper sheet has some slots cut in it. And when we look at the explanation of this, which is an electrical one, it's really important to remember that there are these slots in here, in other words, air gaps that don't conduct electricity. So I've got one more experiment to show you, and one you can do at home as well. You need a piece of thick copper piping, like the type you use for plumbing and radiators and things like that. And then I've got a weight here. It's got some rubber on the ends just so it doesn't bang into my table, but that doesn't matter. So that's the same as the nut. And I've also got another one that looks identical. It's the same mass, but this one is a magnet. Now, I need to remind you that, of course, that copper pipe is not magnetic. So what we'll do is we'll drop the regular weight through the tube, and it's no surprise what happens. It free falls without any friction really at all and comes through the tube very quickly. But of course, what do you think is going to happen when we drop the magnet through the tube? I'm always surprised by when I do this experiment, by just how long it takes to go through. 3, 2, 1, go. Now this is exactly the same effect as we had when we were doing the magnet down the frying pan. That it slides down, but it feels another force which slows down its motion, whereas the normal weight just falls straight through without stopping. So, now's my time to try and give you an explanation. So, I've now got my work cut out to explain what's going on here. It's a bit of an A-level concept, and it goes under the title of Lenz's law. That's nothing to do with the lenses that you might have in your glasses, but some GCSE physics will help us as well. So, brace yourself for an explanation. This is a metal, and it's a conductor of electricity. Our magnet has a magnetic field associated with it, and you might remember that when you move a magnet past a conductor, you induce an EMF in it. You generate a voltage. But because this pan is continuous, that voltage can cause a current to flow in it. And then the final twist is that if a current can flow in the pan's metal, then it will also create a magnetic field, because a current flowing in a conductor has its own magnetic field associated with it. So when the magnet moves down the frying pan, its magnetic field cuts through the metal of the frying pan, creates a voltage in the frying pan which drives a current. That current has its own magnetic field, and the crucial link is the magnetism created by the magnet sliding down the pan and the current flowing through it. Those two magnetic fields oppose each other. So we've got a magnetic field moving down the pan due to the magnet, and we've got a magnetic field due to the electricity or the eddy currents flowing in the pan. And those two magnetic fields will always oppose each other. So when you put the magnet on the pan, it wants to slide down, but the current in the pan with its magnetic field is trying to stop it slide down. This will only work, of course, when the magnet is moving, because that's the only time you will induce a voltage and therefore drive a current through the metal of the pan. So that was quite a difficult explanation. I don't know how much of that you followed, but these two items help us explain it a little bit better as well. If you can remember, the one with all the little fins on it with the slots slid through the magnetic field of the permanent magnet quite freely and didn't feel any braking forces, whereas the solid one did. And it's exactly the same process explained by Lenz's law, that when the solid one cuts through the magnetic field, it induces eddy currents in this one, and those eddy currents have their own magnetic field, which opposes the magnetic field of the permanent magnet. This tries to do exactly the same thing, but the eddy currents can't form, because even though it cuts through the magnetic field of the external magnet, currents can't form here because there aren't continuous loops. And without any current forming in this one, you won't get any magnetic field forming in this one, and so no magnetic field to oppose the magnetic field of the permanent magnet. So whatever happened there, whether you followed the explanation or not, and if you didn't follow it, I blame myself entirely because it is quite difficult to explain. Get yourself a strong magnet, get a frying pan that's made of metal and it isn't magnetic, and just have a play. And you can turn it through quite a large angle, and the magnet itself will slide down really slowly due to this eddy current braking, and something that is just a metal and not a magnet will slide down straight away and not stop. I hope you enjoyed that video, and I look forward to seeing you again next time.